Dear students, now we will learn applications of Laplace transforms to differential equations. Solving differential equations using Laplace transforms involve converting a differential equation into an algebraic equation and then finding a solution for the differential equation using inverse Laplace transforms. I will illustrate by taking a second order linear differential equation with the constant coefficients a, b and c and given condition to be y of 0 is equal to p and y dash of 0 is equal to q. We will recollect the formulas which we have learned so far. L of f dash of t is s times L of f of t minus f of 0, and similarly L of f double dash of t, L of f double dash of t are given like this. In place of f, we can also put y in order to facilitate solving a differential equation where a dependent variable happens to be y. So your new formulas will become L of y dash is equal to s times L of y minus y of 0, and correspondingly L of y double dash is given like this, L of y double dash is given like this. As I said earlier, I will take a second order linear differential equation with the constant coefficients a, b and c, and let us take Laplace transform both the sides so that we will get an expression like this. We will substitute for L of y double dash and L of y dash, and we will get this, where R of s is Laplace transform of R of t. We will simplify this expression further and we will arrive at this expression for L of y. Now how we are going to get y? We will get y by taking inverse Laplace transform both the sides, so that the solution y can be given as L inverse of this expression. We will not use this as a formula, but rather we will see the procedure involved in getting this y. First, we will take Laplace transform both the sides of this differential equation. We will substitute the initial conditions in the formulas and we will arrive at L of y. Then we will simplify right hand side so that inverse Laplace transform can be applied in the right hand side, so that we will get the solution y. Now we are going to see nearly 6 problems, and each problem may introduce something new for us to learn. As a first problem, we will solve this. Y double dash minus 3y dash minus 4y is equal to 2 e to the power minus t, given y of 0 is equal to 1 and y dash of 0 is equal to 1. As I said earlier, we will take Laplace transforms both the sides. We will get this expression and we will substitute for L of y double dash and L of y dash, and right hand side is 1 divided by s plus 1 for L of e to the power minus t. We will substitute the initial conditions and we will simplify this further, and we will get an expression L of y is equal to s square minus s divided by s plus 1 whole square into s minus 4. Now how we are going to get y? Before getting y, we need to convert the right hand side into simple expressions of or simple terms of functions of s. How we are going to do that? Recall from the previous slide, L of y to be the right hand side, and we are now going to apply partial fractions method, so that right hand side can be split into partial fractions in this fashion, where a, b and c are the unknowns which are supposed to be found by using this expression, and we will get a is equal to 13 by 25, b is equal to minus 2 by 5, c is equal to 12 by 25. You can pause this video and you yourself can solve and verify whether you are getting a, b and c like this. And then y can be found by taking inverse Laplace transform both the sides, and we will make use of these formulas which we have learned so far. Just recall, L inverse of f of s plus a is e to the power minus aat into L inverse of f of s. Similarly, L inverse of 1 by s power a is t to the power a minus 1 divided by gamma of a, where gamma of a can be expressed as factorial of a minus 1 if a is a natural number. So we will make use of these formulas so that we will get this as y. Now a, b and c are already found, so that we will substitute a, b and c and we will get the solution like this. Right? Now we shall go for solving second problem. Now consider the second problem, which is solving d square plus 4d plus 13 of y is equal to e to the power minus t sin t, where capital D is given to be d by dt, and initial conditions are given as y of 0 is 0, y dash of 0 is 0. We will convert this differential equation into this form, y double dash plus 4y dash plus 13y is equal to e to the power minus t sin t. Now we will take Laplace transform both the sides. And see the right hand side, we can apply this shifting property. L of e to the power minus at of t is L of f of t, where s is replaced by s plus a. So that this expression we will get. Now we will substitute the given initial conditions, and L of y can be arrived to be 1 divided by s square plus 2s plus 2 into s square plus 4s plus 13. Now at this point, I would like to illustrate you with two methods. We will proceed from here using two methods. First one is using partial fractions. Second one is using convolution theorem. Now we will go for using partial fractions. Let us consider this expression and we will equate this expression as partial fractions involving a, b, c and d. Our aim is now to find out a, b and c and d. So you all know how to find a, b, c and d. We will equate coefficients of s cube both the sides. We will get an expression like this. We will equate coefficient of s square both the sides. We will get like this. We will also equate coefficient of s both the sides. We will get an expression like this. We will also equate coefficient of s power 0. I mean the constant term both the sides. We will get an expression like this. Now you have four expressions involving capital A, capital B, capital C, capital D. Solve these four expressions and we will get the values of A, B, C and D to be like this. You can pause the video now and you can do this problem yourself and verify yourself that you get these four values. Now Laplace transform of y after substituting capital A, capital B, capital C, capital D is given to be this expression. Now our aim is to find out y by finding inverse Laplace transform on the right hand side. So this is what we got in the last side, L of y. Now if you look at L of y, there are two terms. First term denominator has s plus 1, second term denominator has s plus 2. We will convert the first term as a function of s plus 1 and the second term as a function of s plus 2 so that y can be expressed as inverse Laplace transform of this function of s plus 1 plus inverse Laplace transform of this function of s plus 2, so that we can apply this formula L inverse of f of s plus a as e to the power minus at into L inverse of f of s. So that formula we apply here, and for the first term we get e to the power minus t into L inverse of function of s, plus for the second term we get e to the power minus 2t into L inverse of function of s. Now you can verify by working out yourself that y is this expression. The solution is this expression. You can pause the video and work out yourself, convince yourself that you get the solution. Now what is remaining is, by making use of convolution theorem, how to solve the problem once again. Recall what we have found earlier. L of y is 1 divided by s square plus 2s plus 2 into s square plus 2s plus 13. Now how to use convolution theorem? Recall L inverse of f of s into g of s is L inverse of f of s star L inverse of g of s. Here star stands for convolution product. We can write the first term as a function of s plus 1 and the second term as a function of s plus 2. Now we all know how to find inverse Laplace transform of these functions. In the previous slide we have seen the formulas for that, and note that I have applied commutative property of convolution product, so that e to the power minus 2t sin 3t occurs first, e to the power minus t sin t occurs second. Why I am doing that? You see, the convolution product is given as f of t star g of t is integral u is equal to 0 to t f of u g of t minus u du. Note that the output of this integral should be a function of t. Now u is the variable of integration. U is a dummy variable which facilitates the integration. If you notice, the first function, in the first function t is replaced by u, and in the second function t is replaced by t minus u. T minus u a bit complicated function than u in comparison. So in this expression involving product of two functions, e to the power minus 2t sin 3t looks little bit complicated than e to the power minus t sin t. Since e to the power minus t sin t is simpler than the first function, it is better this t is replaced with t minus u, and the first function t is replaced with u, so that after applying this convolution product formula we will get an expression like this. Now if you notice, t is considered to be a constant as far as this integration is considered, so you can take e to the power minus t outside. You will have an expression sin 3u and sin t minus u. I am going to apply sin a sin b formula, which is half cos a minus b minus cos a plus b, so that I will get an expression like this. You can pause the video and check yourself you are getting this or not. Now I just want to caution you with one thing. There are students who will be applying sin a minus b formula for this sin t minus u. If that is the case, you will get some two more expressions, and in that two more expressions you need to once again apply this sin a sin b or cos a cos b, such kind of formulas you need to once again apply, and then you will get nearly 4 terms. But if you apply sin a minus b formula like that, you will get 4 expressions like this, which will be again complicated. Instead of applying sin a minus b formula here, we will combine sin 3u and sin t minus u, and we will apply sin a sin b formula here, so that you will be having only 2 expressions. You need to integrate only twice. Otherwise, you need to integrate nearly 3 times or 4 times depending upon the case. Let us now proceed. Recall, this is the expression which you got in the previous slide and can be simplified, and we will get this. Now you can apply this formula, integral e to the power ax cos bx plus c dx is given to be this expression. You can apply this formula. Otherwise you need to apply integration by parts 2 times. Instead you can apply this formula. So you will get an expression like this. U is equal to 0 to t can be substituted, and finally you will get this, and which can be simplified further, and you will get an expression like this. E to the power minus t is outside, and you can take that inside and get the solution to be like this. You can check yourself by pausing the video and convince yourself that this is the solution we get. Okay, I hope you have learned 2 methods of finding inverse Laplace transforms of the right hand side of L of y function. Right, now we will get into next problem. Now we will consider problem number 3, which is to solve x double dash plus 9x is equal to 18t, given x of 0 is equal to 0, x of pi by 2 is equal to 0, where x dash is dx by dt. Note that unlike in the previous problems, in this problem we are given dependent variable to be x. As usual, independent variable is t. So x is a function of x of t. X is a function of t, and L of x double dash is s square L of x minus s times x of 0 minus x dash of 0. And I want you to note one important thing. See, x dash of 0 is not given. Only x of pi by 2 is equal to 0 is given. In fact, x of 0 is equal to 0 is an initial condition, but x of pi by 2 is equal to 0 is not an initial condition. So one of the initial condition, x dash of 0, is not given. So let's take x dash of 0 is equal to c. Now we will consider the differential equation again, and we will take a Laplace transform both the sides. We will get this expression, and we will substitute the formulas, and we shall put x dash of 0 is equal to c. We will get an expression like this. So L of x is given to be 18 divided by s square into s square plus 9 plus c divided by s square plus 9. So this is the expression we got, and we'll split the first term into 2 terms like this, and we will apply inverse Laplace transform both the sides. We will get an expression involving c. So now the solution for x involves c. X is equal to 2t plus c minus 2 divided by 3 into sin 3t. Now we need to find out the value of c. How we are going to find? You see, x of pi by 2 is equal to 0 is given. Now put t is equal to pi by 2 in equation 1, and we will get c minus 2 divided by 3 as pi, and put that into the equation 1. We will get the solution to be x is equal to 2t plus pi sin 3t. So this is the solution for differential equation when initial condition is not given. Now as fourth problem, we consider this problem y double dash plus 9y is equal to r of t, where y of 0 is 0 and y dash of 0 is 4, and the right hand side r of t is given as the function 8 sin t whenever t is lying between 0 and pi, 0 whenever t is greater than or equal to pi. Now this kind of function can be expressed in terms of unit step function like this: 8 sin t into u of t minus u of t minus pi. You can pause this video at this point and you yourself can verify whether this expression of unit step function gives back the given r of t. And I take this 8 sin t inside and we will get 8 u t sin t minus 8 u of t minus pi into sin of t. This sin of t, now I replaced it like this. I have subtracted pi and then I have added pi, and so that I will get an expression like this: 8 u of t sin t plus 8 u of t minus pi into sin t minus pi. Why I have subtracted pi here and then added pi here? Because you can recollect this formula: Laplace transform of u of t minus a into f of t minus a is e to the power minus as into Laplace transform of f of t. Whenever we wanted to find the Laplace transform of u of t minus a, the function which is beside u of t minus a should also be a function of t minus a. Only then we will be able to find Laplace transform of u of t minus a into f of t minus a to be e to the power minus as into L of f of t. So in the second term here, 8 times u of t minus pi was there and then sin t was there. So in order to make the second function sin t as a function of t minus pi, we have subtracted pi and then we have added pi. So that now the first term is 8 times u of t sin t, which is a function of t, and the second term is 8 times u of t minus pi into sin of t minus pi, which is a function of t minus pi. Now we will be in a position to find Laplace transform of r of t, and using this formula we will get the Laplace transform of r of t to be this expression. Now we will come back to our differential equation y double dash plus 9y is equal to r of t, and take Laplace transform both the sides. We will get this expression. Substituting the formulas, and after substituting Laplace transform of r of t, which we have already found before, we will get this expression, and simplify we will get this expression involving 3 terms. Now recall, we have got Laplace transform of y to be having these 3 terms, and we split first term as well as second term into partial fractions like this. And now we will apply inverse Laplace transform. We will get y to be this expression. Note that the third term involves e to the power minus pi s into function of s, for which we have applied the formula inverse Laplace transform of e to the power minus as fs as u of t minus a into inverse Laplace transform of f of s, where s is t is replaced by t minus a. So in this case t is replaced by t minus pi. So after substituting these, we will get the solution to be this expression. We can pause this video and verify that you get this. We can also write this expression because of the presence of u of t minus pi. We can also write this expression in this fashion. Once again, you pause this video and verify yourself that you indeed get this expression for y, right? Now let us try to solve problem number 5. Now you see, in the problem number 5 we have a linear differential equation but with variable coefficients. Unlike the previous problems which involve constant coefficients, in this problem we consider variable coefficients, and as usual we are given with some condition. Y of 0 is equal to 1 is an initial condition, but y of pi is equal to 0 is not an initial condition. Okay, but anyhow, let us see how to proceed. Take Laplace transform both the sides, so we will get this expression. And you see, Laplace transform of t times y double dash, that is given by this expression minus d by ds into L of y double dash. You know, Laplace transform of t times f of t is given to be minus d by ds of Laplace transform of f of t. That is the formula which we apply here. And you also have derivative of Laplace transform of y double dash. Now if you substitute Laplace transform of y double dash here, we will get this expression. Now I am going to replace L of y as capital Y of s. Why I am doing that? Because you have a derivative d by ds operator. So which is a differential operator going to differentiate with respect to s. For that purpose, L of y is replaced as capital Y of s. In fact, Laplace transform of y is nothing but a function of s. We denote Laplace transform of small y as capital Y of s. And now make use of the initial condition and substitute that. We can simplify and we will get y dash of s, that is capital Y dash of s, is equal to minus 1 divided by s square plus 1. You can pause this video here and verify yourself that this is the expression you get. Recall, this is the expression you got for y dash s, and solving this differential equation. You see, this is a differential equation. We are going to solve this differential equation. We are not going to apply inverse Laplace transform here. We are going to solve this differential equation to get y of s. So y of s is cot inverse of s plus constant. By solving this differential equation, we are forced to introduce a constant c. Now it is a burden for us to find the value of c. You see, by taking limit s tends to infinity both the sides, we will get 0 is equal to 0 plus c. Why? Because we know whenever s tends to infinity, Laplace transform will tend to 0. That property we have already come across in the initial stages of our classes. So now we are able to find the value of c, which is 0. So capital Y of s is cot inverse s. Now we need to find out y, small y. Small y is nothing but L inverse of y. L inverse of y of s. So small y is L inverse of capital Y of s, which is L inverse of cot inverse of s, which is minus 1 by t, L inverse of minus 1 by s square plus 1. Recollect that property which we have learned earlier. And now you can see the solution is given as y is equal to sin t by t. So as of now, you know how to solve a differential equation even if a variable is involved in the differential equation. Now as a last problem, we see this problem number 6. Solve the integral differential equation y dash plus 5y plus 4 times integral 0 to t y dt is equal to e to the power minus t given y of 0 is equal to 0. Why this is called as integral differential equation? Because the first two terms involve y dash plus 5y, which is part of differential equation, and the third term involve integral 0 to t y dt, which is an integral of y. So because of which this equation is called as integral differential equation. So how we are going to solve? As usual, we are going to take Laplace transform both the sides, because we are equipped with formula for finding Laplace transform of integrals. You see, by taking Laplace transform both the sides, we get an expression like this, and the third term is 4 times Laplace transform of integral 0 to t y dt. We all know that one is equal to 1 by s Laplace transform of f of t. So substitute this and simplify, you will get this expression for L of y. And you can pause this video and check yourself that you indeed get this. Now how we are going to proceed? As usual, we will be splitting the right hand side into partial fractions, and then we will apply inverse Laplace transforms formulas so that we will get the solution to be this. You can once again pause this video here and verify yourself that you indeed get this as solution. So students, now we have come across nearly 6 problems, and you are equipped with techniques for solving differential equations using Laplace transforms. Now this is the time for you to implement whatever knowledge you have gained so far. So I am going to give some problems as practice so that you can practice these techniques and you can gain confidence on solving differential equations using Laplace transforms. So the practice problems involve around 5 problems. The first problem is this simple differential equation, which is very easy for you at this stage because you have already come across 6 problems, and the second one involve third order differential equation, which is again easy for you because you just need to substitute the formula of L of y triple dash. And the third problem is not an initial value problem because y of pi by 2 is equal to minus 1, but similar problem we have already solved. So if you solve this problem, you will gain much more confidence. And the fourth problem, if you notice, it is again a second order differential equation, but the right hand side function is not a usual function, it is a Dirac delta function. And you all know how to find the Laplace transform of Dirac delta function. So simply take Laplace transform both the sides, you will get L of y, and from where you can apply inverse Laplace transforms and get the solution. The fifth problem is an integral differential equation, but we cannot say it is an integral differential equation because derivative of x is not involved. So it's an integral equation. In this integral equation, if you notice the second term of right hand side, this is nothing but convolution of x of t and sin t. So by making use of convolution concept and by making use of taking Laplace transform both the sides, you can get the solution, right? So now you are given 5 problems. You solve those 5 problems and try to get the solutions for this. How to verify whether you got correct solutions or not, you see the next slide. Hope you have attempted solving the problems posed in the previous slide. Now the answers for the previous slides practice problems are given here, and if your answers are all correct, you have really gained confidence on solving differential equations using Laplace transforms. If you are wrong, don't lose heart. Once again you try until you gain the confidence of solving all the problems correctly. Hope you enjoy this class. Thank you. Thank you for listening. Bye.